Hello, welcome everybody once more to the Future Leaders in Robotics and AI seminar series brought to you by the Maryland Robotics Center at the University of Maryland. If you just joined us, the purpose of this seminar series is really to promote the innovation of early career researchers in robotics and AI. We have a full slate of presenters for this spring, and you can find that information at robotics.umd.edu/future leaders. You can also find previous recordings for previous semesters, and you can use the website to nominate anybody that might be interested in presenting in the future. So we just heard from Professor Ruth Mirsky. Our next presenter is Yewei Huang. She's a PhD candidate studying at Stevens Institute of Technology in the Department of Mechanical Engineering. Yewei received both a bachelor's degree in Geographic Information Systems and a master's degree in Surveying and Mapping from Tongji University. Her research interests include distributed multi-robot systems, marine robotics, and robot navigation and decision-making. Okay. So I'm looking forward to the presentation, and with that, I'll stop sharing so Yewei can share her screen.
Okay, can you hear me?
Yes.
Awesome, I will share my screen. Hi, everyone. I'm Yewei Huang from Stevens Institute of Technology. I'm really happy today I have the opportunity to share my previous and recent work on data-efficient localization and mapping for distributed multi-robot teams in the field with all of you. So let's start with motivation. So why we choose multi-robot teams when we can deal with only a single robot, since it's obvious that using a single robot is much easier. That's because multi-robot teams can be much more efficient than using a single robot in a lot of time-sensitive or collaborative tasks. For example, rescuing after disasters, when there is earthquake or forest fires, if you have a team of robots that helping you with the rescuing, that will be help a lot. And the robot teams can be also very useful for help us exploring some dangerous areas. For example, the outer space, the moon, the Mars, and also the desert, and even some areas that's contaminated by nuclear wastes. And the multi-robot teams can also help humans to do tasks that they are unwilling to do, for example, the agricultural and the construction services. So humans don't need to work under the sun during summer. And perception is playing definitely a crucial role for not only a single robot, but also multi-robot teams, since perception is kind of the eye for robots. If robots are blind, they won't be like doing all the work efficiently. So the perception can ensure the robot to navigate safely, since they can help with obstacle avoidance, and also the map built from the sensor data collected by the robot and its team members can supporting the future task location. And in my perspective, maybe others have other opinion, but the core perception module for the exploration of the unknown environments is definitely simultaneous localization and mapping, also known as SLAM. SLAM is a robotics technique that enables a robot to map an unknown environment that while simultaneously tracking its own location within that map. So the robot is kind of dropped into an unknown location, for example, on the Mars, and it have no idea where it is, but it have to figure out where it is and how the environment is look like. And the biggest difference between multi-robot SLAM and single robot SLAM is there will be multiple robots exploring this exact area. So they have to exchange their data and try to merge their map into a global map. This is called inter-robot data association, or the map merging from the local robot frame to the global robot frame. There is still a lot of challenges in multi-robot SLAM. The biggest challenge is definitely limited communication bandwidth. And there is a lot of problem actually coming from this limited communication bandwidth. For example, since we don't have enough communication bandwidth to exchange all data we have with our team member, so we can't calculate accurate geometric information for our map merging. And because we don't have a limited communication bandwidth, we may have have been a delay on communicating with our team members. So there's problem with map consistency, or our system may false because of this communication bandwidth problem. So this problem can't help but come into our mind. How can we perform multi-robot SLAM efficiently and effectively when we only have this limited communication bandwidth? So we try to dig a little bit deeper into this problem. And here is 3 different trials of us trying to dive deeper into this problem. So we first proposed DiscoSLAM, which is a distributed multi-robot SLAM framework using a compact LiDAR descriptor. And the name of the descriptor is actually where SC comes from. And we also propose a 2-stage global and local factor graph optimization. And then, since these days, with the development of all the fancy and helpful computer vision and large language model technologies, we want to have a map that not only benefit the robot teams for the task, and also maybe can get our human involved. So we propose this SGM SLAM, where SGM is for scene graph matching. So we are using scene graph data structure in our SLAM. And then we go a little bit further, and instead of doing SLAM on the solid land, we went into ocean. We tried to develop this Draco SLAM 2, which is using a similar scene graph matching technique. However, we add a robust loop closure selection, which we call group-wise consistent measurement set maximization, GCM, which is inspired by a really famous algorithm for outlier detection in the multi-robot area, which is called PCM, and we will talk about all of them later. So let's start with the DiscoSLAM. DiscoSLAM is actually a earlier work where I published in IEEE RAL in 2022. And this is a data efficient communication SLAM method using scan context descriptor, which is a compact LiDAR descriptor to answer the limited communication bandwidth problem. And we also propose this 2-stage global local optimization to ensure the robustness to failure and to avoid the delay of the robots. So in the global optimization step, we try to calculate a high quality initial guess for the map transformation. And in the local optimization part, we use that exact map transformation estimated in the global optimization part and ensure a stable and accurate local growth graph. Here, the small video on the right-hand side showing the map merging result before and after the global optimization happens. Now the yellow cloud is the yellow cloud is now merged into the global map. So the single robot SLAM problem is actually trying to solve a maximum A posterior problem, MAP problem, with all the constraints related to the single robot itself involved. However, for the multi-robot SLAM, we have not only constraint from the single robot, which we call it F intra, but also the constraint from between robots, for example, robot A and B, robot A and C, robot B and C, which we call it F inter. Since we want to solve it in a distributed manner, we try to distribute the task to all the local robots. So we rewrite the constraint for each robot. There is still the intra-robot part and inter-robot part. For the intra-robot part, there is only all the constraint with the robot itself involved, while for the inter-robot part, only the constraint between robot itself and the other robot is involved. For example, if there is ABC through robot, for robot A, we have constraint between robot A and robot B and robot A and robot C, but we don't care what's happening with robot B and C. By using this module, we can kind of lower the computation burden for the local robot. However, we definitely sacrifice a little bit accuracy here. So we come up with this 2-stage global local optimization. In the global optimization part, we try our best to estimate the relative transformation from the local robot frame into the global robot frame. While in the local estimation part, we just set the multi-robot problem alone and try our best to have a stable estimation of all our history robot states. Here is an overview of the architecture of the Disco SLAM system, and all the multi-robot SLAM I will be talking later all share a similar architecture. So here, when the local robot, here is local robot alpha, receive a scan contact feature from the neighbor robots, the KD tree search is performed. And if we detect a look closer candidate, we try to perform ICP post estimation. When we get a series of loop closure candidates, we perform PCM for the outlier detection. And all the relative transformations that accepted by PCM will be transformed to this transformation optimization step, where the global optimization happens. After that, the global optimization result, the relative transformation from local robot to the global frame, is used for the local SLAM, which we call the local optimization. And then we can have like a stable state estimation of our history and also our related relationship between local frame and the global frame. Here we show some results of our proposed Disco SLAM with 3 different configurations, where our full configuration, our partial configurations. This is a dataset collected by our JACO ground vehicle in a park, so we call it a park dataset. So it looks similar from the bird eye view. However, if we rotate them, you can see the full global and local optimization definitely works better than like a half module. We also tried our pipeline on some classical K data set and also another data set we collected a while ago on the Stevens campus. See, our algorithm is kind of working nicely. Most of them. Well, I personally like Disco SLAM. However, it's kind of hard to distinguish everything from the point cloud map. So with the development of computer vision language model, large language model, I can't help but think about how can we push all this kind of fancy stuff into SLAM so we can make SLAM fancy again. And this comes into my mind, the scene graph SLAM. The benefit of using a scene graph is twofold. First of all, with a scene graph structure, which is lightweight hierarchical, we can achieve a much more data efficient communication with only exchange the scene graph between robots. And not to say scene graph is a description of the whole map, which have much more rich information than the compact LiDAR descriptor we used to use. And the straightforward and inherently structured scene graph structure made it easier to interact with. For example, we can imagine if we have this multi-layer map and we can zoom in and zoom out, feeling like we are just in that environment, even if we are like miles away. Here is an overview of the architecture of our scene graph SLAM system. As I mentioned before, it's kind of similar, and the most important difference here is how we do the inter-robot data association. Here, instead of exchange the compare LiDAR descriptor with our team members, we exchange a scene graph with our team members, and we perform a scene graph level matching to get the relative transformation between the local robot frame and the global robot frame. Here is a simple illustration of how we get the single robot scene graph constructed. First, we have the images that we captured with a camera, and we do the image segmentation with one former. And then we try to align the segmented image with the point cloud. Then this point cloud is labeled with semantic information. We use this point cloud to do the object clustering. And then we consider this intra-robot data association problem as a linear assignment problem, LAP problem. So the objects can be distinguished from each other. And then we get the scene graph of a single robot building in a room. You can see here the gray indicates this is a room. here the red is all the tables here in the room, all the green are the doors in the room, and we have two layers in this graph, which is keyframe layer and object layer, both connected with edges indicating their relationship. For example, when an object is observed by a keyframe, they are connected with each other. After we build the scene graph, we exchange the scene graph with each other, and then we perform our inter-robot scene graph comparison. Here is the utility function for our comparison. There is vertex-wise comparison that involves the comparison between the type of the vertices, and there is also edge-wise comparison that for this version of our algorithm, it's on edge-wise comparison is only comparing the relative Euclidean distance between the objects inside the scene graph. However, in the future, we can definitely expand this edge-wise comparison to, for example, comparing their relationship, whether the laptop is on the table, the laptop is under the table, the laptop is open, the laptop is closed. This kind of semantic information can also be fused into this utility function. And we, by doing some magical math with the eigenvariables and eigenvectors, we can convert this QAP problem into a LAP problem and solve it in a similar manner as we do for the intra-robot case. And we perform some simulation test with our proposed algorithm, and we prove the algorithm work even when there is error involved in both semantic information and the localization information. Here, we also collect some data on the SRI International Campus in Princeton. In this data set, two robots, which is the unitary robot dog, is involved and collect data in some kind of park-like environment. And two robots are shown in red and blue. Their vision is shown in the RGB color, while the mapped environment is shown with the LiDAR intensity. Here we can see the scene graph matching is already performed. And when the system thinks there is sufficient number of objects merge with each other, it starts to do the transformation estimation, which will happen soon. And then after the transformation estimation, the robots try to fix the relative relationship between all the objects, and the object map is then merged. Okay, and then we try to dive a little bit further into the ocean. Multi-robot team is actually especially useful for the underwater environment, since the marine missions are always large scale. Every time we try to publish a paper for the marine environment, they always ask why your environment is so small. And all the marine missions are always long-term. You don't want to be like every day going onto the ocean and then deploy some sensors and then get it today. You want it to do long-term environment monitoring for you. And the communication bandwidth is especially a problem for the marine environment, since the widely used acoustic modems for the marine environment only have 62.5 kbps bandwidth, which is like, sounds like crazy in the modern time, but that's a problem for the marine environment. And here we select sonar as our sensor because sonar definitely works better than vision in monkey waters. And we have a lot of monkey water in Hudson River, which is next to our campus. So we actually don't have a choice. However, the introduction of sonar sensor raised some new challenge because of the acoustic noise. And now we have some difficulty with the scan registration. So we try to answer this question by using Draco SLAM 2, which is a multi-robot SLAM algorithm featuring object graph matching. the similar object graph matching technique we use in ZSGM matching. However, this is kind of a breakthrough for us for the marine environment because this object graph matching enable us to get a reliable initial guess for the ICP scan registration and making the ICP scan registration like 10 times or even more faster. So we can find more loop closures in a computational efficiency manner. And since we find there is some special similar registration error happening for the marine environment, as shown in red here, we propose this group-wise consistent measurement set maximization algorithm, which we call GCM, to try to detect the outliers. And here is an overview of the Draco SLAM 2 pipeline. The main difference here is we are using sonar image for all the feature extraction and alignment. And another big improvement here is we use the GCM as the outlier rejection. Here is our motivation for GCM. You can see in the ideal world, we want the ICP scan registration to magically help us align the target scan and the source scan perfectly. However, in real world, we have this kind of annoying similar point cloud registration errors that happen for the marine environment. That's really hard to avoid because me as a human can distinguish whether it's correct or not from these single images. So inspired by the well-known PCM algorithm, we check the interrobot constraint between robots pairwisely. So there's 2 robots involved for PCM. We add the relative transformation between local frame and global frame from the scene graph matching into the outlier detection module and try to check the consistency of all these interrobot loop closures group-wisely. So for PCM, if I have 3 robots, alpha, beta, and gamma, I have to do alpha and beta, alpha and gamma if I'm the local robot alpha. However, for GCM, I can try to find outliers using all information from alpha, beta, and gamma, and that kind of ensure a better performance. And here is some of the performance of our algorithm on this airplane simulation dataset that we collected using HoloOcean. Here is another dataset we actually collected a while ago in the US Merchant Marine Academy. So we call it the USMMA dataset. I say there's still a large difference between the real sonar image and the simulated sonar image, while the real sonar image is definitely much more blurry. So for the future work, I definitely still want to work on this autonomous exploration for the real marine environment. I hope in the future I can integrating actually Draco SLAM 2 on the blue ROVs we have and making them explore the real world environment like. And for the scene graph matching part, since we already have a nice scene graph matching SLAM algorithm, I hope we can do some further work on motion planning and decision making using the recent technology of large language models. So our robot dog can actually help people with all their family choices, and maybe they can compete with our Jekyll ground vehicles. And that's all for my presentation today. I want to thank you all you guys for listening to it. And I also want to thank you, my RFAL lab, for giving me such a nice opportunity to do all this research. And by the way, since I'm already almost graduate, if you want some SLAM guy in your lab, please let me know. And that's all for my presentation.
Thank you so much, Yewei. That was a very interesting presentation. It's almost 3 o'clock, so we have time for a couple of questions. If anybody has a question, please use the Q&A feature to ask your question. Yes, Michael.
I guess I have a question, and I could just ask it directly. So, is my microphone? Can you hear me?
Yeah,
Yes.
yeah, I can hear you.
Okay. Okay. So the idea of the semantic stuff for SLAM is super interesting to me, and I saw like early on in the talk on like slide 5, it kind of was outlined in green, and you talked a little bit more about it starting on maybe slide 11. But I'm still kind of confused about how does one kind of tune the difference between semantic closeness and like kind of apparent spatial closeness for your SLAM algorithm? Is there like tuning parameters, or is there some other way to do this?
So we are using kind of it's kind of like a gate. If they have like the same relationship, we set the gate to be like pars, but if like the relationship is wrong, we set the gate to be closed.
Okay, and then so for each kind of semantically defined object, apologies if I'm using the wrong words, do you kind of use like a centroid of that thing as like the location of that?
Yeah, that's actually what I do for this algorithm.
Okay, awesome, thank you.
Thank you so much. I have a couple questions in the Q&A. The first one is human perception and robot perception the same? This is for Deependra Yadav.
The human perception and
Because how would you compare, right, the perception between human and robot?
Oh, the human perception and robot perception. I think they are definitely really large different. It's kind of we are on our way to trying to make robot perceive in a much similar manner as human do, but we are still on our way of trying it. And SimGraph is kind of our trial of doing it, since human definitely not see the world as a point cloud, but kind of when you see a pencil, you just know it's a pencil.
Right. Yeah, that's one maybe last question from Sarah Honorable. She says, very interesting presentation. Could you please clarify how you would construct an interaction graph for your multi-robot system and how you would integrate the scene graph for multiple robots?
Oh, that's a long question, long problem. So we first do image segmentation, and then we do alignment, and we build the local robots in graph, and then we get relative transformation, and we use transformation to actually merge the objects. And since the objects are associated with keyframes, we use that information to then align the keyframe. And also the semantic point cloud we have here. So it's kind of everything. First, the object layer is aligned, and with the information we get from aligning the object layer, we align the keyframe layer. And after keyframe layer is aligned, the semantic layer and the fused point cloud is also aligned. It's just because they are all connected with edges, this just can happen like one by one. Yeah.
Thank you. Hopefully that answered the question. I think in the interest of time, we're going to stop the recording. I want to thank everybody for coming and let you know that we have another one of these presentations coming up in a couple of weeks. Again, please go to the website, which I'm going to bring up the link in a second. So you can see all the presentations that we have lined up, as well as previous presentation recordings and nominate future speakers. Thank you all.